Okay, let's look and see what we have here in external respiration. Of course, the respiration happening from the lungs. Here's a part of an alveolus right here. Here's our respiratory membrane, a very thin area. Here I've got a partial pressure of 104 millimeters of mercury for oxygen, a partial pressure of 40 millimeters of mercury for carbon dioxide in my alveolus. For the blood coming in here through my pulmonary arteries branching down through my capillaries, my oxygen is 40 millimeters of mercury, so it's much less here than it is here. But my carbon dioxide is 45 millimeters of mercury, which means it's a little bit more here than here. Now, of course, all this is happening at the same time, but obviously oxygen, since it's so low here and so high here, it's going to move from high to low till it reaches equilibrium. Carbon dioxide, on the other hand, is going to move from here to here because it's higher here than here. So again, it's going to move from high to low. But notice, because oxygen is much less soluble, I need a bigger pressure difference before it will actually move to equilibrium. Here, I have a pressure difference of only 5, so it's going to move, because carbon dioxide is very soluble. In other words, it moves from the fluid, the plasma of the blood, into the space of the alveoli very easily, where oxygen is not very soluble, so it needs more pressure gradient difference to be able to do that. Okay, now you may have to adjust your volume because I realized I had my volume on my recorder way too loud, so it picks up every little noise, every little bump on the computer. So anyway, I adjusted it, so you'll probably have to turn your volume up now. Okay, so the next thing we want to look at is a phenomenon called ventilation-perfusion coupling. Okay, so ventilation-perfusion coupling. First, there's actually 4 factors that we have to take into consideration. So 2 of the factors are going to be factors dealing with oxygen, and 2 of them are going to be factors dealing with carbon dioxide. Okay, but what this basically does is the ventilation-perfusion coupling it basically facilitates the gas exchange by maintaining alveolar airflow that's proportional to the blood flow. So if I have a lot of air coming to this alveolus or this whole alveolar sac, then I want a lot of blood going there. Let's say something's doing, I've got a tumor growing in here, I've got something mucus build up in here, I've got something blocking that air exchange here, then I'm going to actually do something with my blood. I'm also going to do something with the smooth muscle to basically contract the actual bronchial areas or cause them to dilate according to how much of the air is flowing in or out. Now, in a situation where I have a lot of airflow going to a region, then my blood vessels running to that area, the arterioles, now remember we're talking about pulmonary blood, so arterioles are oxygen poor blood vessels. So our arterioles are going to vasodilate, because if I have a lot of oxygen flowing in this area, then I want to have a lot of blood to pick up that oxygen. So we see now that this blood vessel has dilated. Now it has the ability to pick up more oxygen once it gets to the alveoli, because we're sending more blood to that area.
Oxygen.
But what if we had something blocking that air's ability to come here? Then we would have a low air supply, so our arterioles would constrict, because since I'm not getting much air in this area, I don't want so much blood flow going to this area because I don't have that much oxygen to pick up. So when we have a high partial pressure of oxygen, our arterioles are going to dilate. When we have a low, as we see in this picture, partial pressure of oxygen, then our arterioles are going to constrict. So our arterioles, the blood vessels bringing oxygen poor blood to the capillaries, they respond to the changes in our partial pressure of oxygen. Again, if I have a lot of oxygen, then my arterioles will dilate. If I have something blocking the flow of oxygen in, then my arterioles are going to constrict. But my bronchioles, the size of my bronchioles, are going to respond to the changes of my partial pressure of my carbon dioxide. Okay, now again, we said that the arterioles respond to the amount of oxygen. If I have a lot of oxygen coming in, the arterioles will dilate. If I don't have as much oxygen coming in due to a blockage or something, the arterioles constrict. But the bronchioles, they respond to the carbon dioxide. Okay, so let's say that obviously carbon dioxide will build up if something is blocking the bronchioles because it can't leave properly. So if carbon dioxide builds up, then I literally want those bronchioles to dilate to give it more room to leave. Okay, so bronchioles will dilate if the carbon dioxide builds up so it can leave. If the bronchioles can remain at a normal size if the carbon dioxide is leaving properly. So looking at this, assume that the ventilation to an alveolar sac is low due to a small tumor. So we've got a small tumor in here and it's blocking air from coming in. So what's going to happen is our oxygen is going to decrease because it can't get in. So the oxygen is not replenished. The partial pressure of carbon dioxide is going to increase because it's hard for it to get eliminated. So what's this going to do? What effect is this going to have on this perfusion coupling that we're talking about? So our arterioles will constrict because we don't want to send more blood there if we're not getting much oxygen in. But our bronchioles, then we want them to dilate, want them to get bigger so we can get that carbon dioxide out of there. We don't want that carbon dioxide to build up. So our answer would be our arterioles would constrict, our bronchioles would dilate. Okay, again here we see the arteriole constricting. Here's our tumor that's blocking the oxygen coming in and the carbon dioxide leaving. So our solution to that would be to let's limit the blood supply coming here right now. Let's constrict our arterioles because we don't have much oxygen to put in them. And let's make this bigger so the carbon dioxide that is there can actually leave. Whereas external respiration is what's going on in the lungs, particularly at the capillary next to the alveoli. Well, what happens once we get into the body? Well, we have our internal respiration, and we're going to obviously deliver oxygen to our cells and then take carbon dioxide away from our cells. But it's still based on this partial pressure gradient difference. Now, we've gone from 104 down to 100 because of imperfect perfusion coupling mechanisms, but we're still at a pretty high pressure for oxygen. So it's higher here than it is here. And the reason why it's not high here is because the cells are constantly using oxygen through cellular respiration. So once oxygen goes in, it starts using it up, therefore the pressure drops. Well, if we have a partial pressure of about 40 and I've got blood bringing oxygen with a partial pressure of 100, then obviously it's going to go from the higher to the lower. Well, in the meantime, we're changing our glucose into carbon dioxide and we're building up our partial pressure of carbon dioxide inside the cells. So as long as the partial pressure of carbon dioxide inside the cell is greater than the partial pressure of carbon dioxide in the blood, then carbon dioxide leaves and goes into the blood. Of course, this is mainly occurring at the capillaries that are next to the tissues. Now, we do have to understand that the rate at which cells use up oxygen is dependent on how active they are. A muscle cell that's active is going to use up a lot more oxygen than almost any other type of cell. Let's compare it to probably, let's say, an adipocyte. An adipocyte probably needs oxygen because it's a living cell, but it doesn't need a lot of oxygen. Therefore, its partial pressure of oxygen is going to be much higher than a muscle cell. Therefore, the bigger the gradient difference, the more oxygen is going to go into that. Even an active muscle cell will use up the oxygen, therefore the pressure will drop more compared to an inactive muscle cell. They both will need oxygen, but the active muscle cell will take in much more oxygen from the blood because it creates a much bigger gradient between the partial pressure of the oxygen in the blood versus the partial pressure of the oxygen in the cell, which is dependent on how fast the cell is using up that oxygen. So again, we can see oxygen went from 100 and it went from high to low to 40, and then it reached equilibrium at 40. We can see carbon dioxide went from 45 into the blood because it was 40, so it went from 45 to 45 because it replaced that lower carbon dioxide content. So all we're really doing is we're just saying things go from high to low until they reach equilibrium. Things go from high to low until it reaches equilibrium. And so it does the same thing in the tissues, but it's just that it's moving from the blood. So in this case, oxygen is unloading from the blood. Carbon dioxide is loading into the blood. Remember, and I can't overemphasize this, when we say loading or unloading, it's always in relationship to the blood. Oxygen unloading from the blood, carbon dioxide loading into the blood. Because you're going to see test questions, it's going to say, where does this occur? Oxygen loading. Where does this occur? Carbon dioxide unloading. And it's always referring to the blood. So here, oxygen is unloading from the blood in the tissues and in internal respiration. Carbon dioxide is loading into the blood in internal respiration at the tissues. Well, earlier we talked about the fact that our partial pressure of nitrogen was the highest partial pressure in the air we breathe, but yet it doesn't really affect us that much in normal circumstances, and the reason is because it has such a low solubility. It takes so much pressure to actually push it into the blood. But most of us have probably heard of something that is often referred to as the bends. What happens, when somebody goes deep sea diving and then they come up too fast? Well, that pressure change of them coming up too fast actually starts forcing nitrogen into the blood, and if they come up too fast, it doesn't have a chance to come out, so they actually have to go decompress, or that will actually start bubbling in their blood and can end up killing somebody. So again, it really all boils down to that partial pressure of nitrogen, and it's such a low solubility, a much lower solubility than even oxygen. Now remember, carbon dioxide has the greatest solubility. It moves the easiest. It doesn't take much pressure to move it. Oxygen has a much bigger solubility, but nitrogen has the most. So the only time we really have to worry about nitrogen is when we're placed under tremendous pressures, which could happen when you're underwater, and the environment there would create that pressure, which would cause nitrogen to be pushed into your blood, and if you come up too fast, it doesn't have a chance to escape. As we see in our explanation here, the diver descends, the pressure within her lungs increases. This increases the partial pressure of nitrogen so that more nitrogen enters the blood. As the diver returns to the surface, the partial pressure decreases. If she rose too rapidly, the relatively insoluble nitrogen would leave the body fluids, forming bubbles. This would result in serious condition known as decompression sickness, or the bends. That's why she'd have to go into a decompression chamber so it could come out of the blood easier.